Hirst Lecture 2024, given by the winner of the joint London Mathematical Society and British Society of the History of Mathematics Hirst Prize and Lectureship 2023, Professor Erhard Scholz. Professor Scholz specializes in the history of mathematics of the 19th and 20th century, historical perspective on the philosophy of mathematics and science, and in particular Hermann Weyl's geometrical methods applied to gravitational theory. He studied mathematics at the University of Bonn and the University of Warwick from 1968 to 1975, and in 1979 he completed his PhD at the University of Bonn before joining the University of Wuppertal as professor, where he was also one of the founders of the Interdisciplinary Center for Science and Technology Studies. Scholz was an invited speaker of the International Congress of Mathematicians in 1994 in Zurich. So please join me now in welcoming our first speaker.
So thank you very much to the London Mathematical Society and the British Society for the History of Mathematics in honoring me to give this talk and to receive that prize, of course. Yeah. Yeah, very good. My talk has somehow as a background a quotation of this type of Michael Atiyah. Here, Michael Atiyah, when he discussed in the 70s and 80s the relationship between mathematics and physics in several places, stated something like this: Maxwell's equations actually motivated Hodge for his work on harmonic forms in general. As indicated, of course, they had explained it before, Maxwell's equations are about forms of degree 2 in 4 dimensions, relativistic Maxwell's equations, and Hodge went to forms of any degree q in any dimension n. And of course, that's a question one could ask. That's a statement one could ask a question. And the question, is this a historical statement? Or is it a mathematical interpretation? Just reading it, it's you cannot really decide. And I should perhaps say, in Wuppertal, there was for several years a broader project on the history of duality in mathematics in different aspects. And one of the organizers, Ralph Krömer, once asked me what I thought about that quotation. So I want to discuss, in a way that's the background. The motivation for my talk is this quote by Atiyah, if you want to stylize it. And in order to historize I have to go, and we have to go back in the late 19th century, in the earliest 20th century, namely Grassmann's, oh, that's difficult to handle. Grassmann's complements of alternating products. And then the rise of Hodge theory, only the rise. I mean, the very beginnings in Hodge's words. I admitted that I will stop at 1950, roughly. And then in the end, I will discuss the Maxwell equation, classical and relativistic, in particular in Hodge's work, but not only. So that's already the schedule of my talk, more or less. And there will be a very short resume. Okay, so we start with Grassmann complements. Here's Hermann Günther Grassmann. And most of you know that he wrote 2 books on the so-called extension theory, Ausdehnungsgrössen, one in 1844, which is rather philosophical in the way of posing the theory, and the second one, which is easier to read for mathematicians because it's more formalized, that's the extension theory of 1862. And the point which I will draw from Grassmann is from the second one, from 1862. Just to indicate there's an interesting background, which I don't discuss here. I have discussed it at other places, for Grassmann's development of extension theory, Ausdehnungsgrössen. And that was work in crystallography, which he did in continuation of his father's work. And just to add to it, his father, Julius Günther Grassmann, in the study of the symmetry of crystals, had developed a symbolism which looks very much like vectorial calculation over the natural numbers. You would say a module over the natural numbers. But that's not part of my story here. In the Ausdehnungsgrössen of 1862, cannot see it. I don't see it. He introduced the so-called extensive quantities, the Ausdehnungsgrössen of any level, in a way which looks very well known to us, just as a linear combination of some fundamental units. He called it the original units. And at the beginning, they were real numbers, rational numbers. Later, they were also complex numbers. And he introduced the operations which look very much like vectorial operations, if we rephrase it in more modernized terms, which was done historically by Peano in 1888. And I jumped directly in the second part of the Ausdehnungslehre because he was interested in products, and particularly in alternating products of his extended quantities. And he called it the combinatorial or exterior products. And so if you start from K, Ausdehnungsgrössen extensive quantities, or not necessarily the units, but already the linear combinations, you build the alternating products. And he called it the quantities of the K level. And he added a unit convention that is small but important. The unit convention was the combinatorial product of all original units, the EIs, is considered to be equal what he called the numerical unit, the numerical unit. So this means this alternating product of the base element, we would say, is he identified with one, which from the modern point of reading, he worked with an alternating product, if we rephrase it in terms of vectorial terminology, of lambda kv with lambda lv and lambda k plus lv. And he chose a volume form indirectly. I mean, in fact, that's not a linear form, but it's the extended quantities themselves, but never mind. It's essentially the choice of a volume form in the alternating product of the level m. And if I write here in this low red, that's just to signal that this is now really a modernized expression. That's somehow anachronistic, but it helps us to easily understand what's going on in the old stuff. Okay, so for a unit of the kth level from lambda k of the vector space, for the unit, he defined the complement, and the complement, E prime, that's his notation, is the combinatorial product of all units not appearing in E itself. This is E prime. You just take the complementary original units or base elements, and with sign such that E times E prime is the absolute unit. One can easily modernize it. The complement, that Grassmann wrote it with this slash E. It's just the complementary units, and you have just to plug in the right sign. That's it. So for a general unit extended quantity of kth level, which is of course a linear combination what do you do? Or what did he do? Obviously, he chose a linear combination of forming the complements. So, that should be in deep red. That's an anachronistic way of writing what he did. What he did was that he mapped the lambda k of V to the lambda n minus k of V. That is a linear version of what later became Hodge duality. That's in 1862. Okay. Hodge duality in the sense of the Hodge star operator, to be frank, because there is a different aspect of Hodge duality as well. Okay, and he didn't use the word dual or duality, he used the word complement. But what he showed is, if you take the double complement, then you come back to the original one, perhaps with a sign. And that is known from the Hodge star operator, for those who know it. Okay. And he introduced products for his extensive quantities of any level, K and L. And by continuation, the alternating product rules. And of course, that's easy for us immediately. What we do still do with the lambda k lambda l, when k plus a is smaller or equal than n, and he called it the progressive product in this case. But if the sum of the levels transcends n, he called it a regressive product. What is a progressive product? I rewrote it. That should be in deep red again. You reduce the level above n by reducing, taking the unit convention. So that's the regressive product. And that was general definition, which has the result. That's again Grassmann's notation. If you take the complement of any time of alternating product, it's the product of the complements. And that works for any level because of this reduction. If you have sum larger than n, and he defined an interior product for AB of any level, K and L, just by taking A alternating product with the complement of B. Then, of course, the level of this product is n plus K minus L for L larger than K, and K minus L otherwise. This means the level is 0 for equal L. That means that's a numerical quantity. And so we had an interior product, which in the case K plus L equal 1 was just identical if you reduce dimension to 3 to the scalar product in the quaternions developed by Hamilton. But his interior product was a bit more general. That's not important, but you see, it was really deeply interrelated with his understanding and forming of the complements. So it's not just by adding some independent stuff just to see what he did with his complements. The result of this definition is now in our reading that the original units, the base elements, they formed an orthonormal basis. So that's quite interesting. And of course, for K equal and for the levels 1 and in 3 dimensions, Grassmann's interior product was the same as Hamilton's scalar product of purely vectorial quantities. Okay, a very short look at the reception of Grassmann. And of course, I cut out one aspect of Grassmann, the complements, because they are at the core of my story. Gibbs had interest in Grassmann's expression of Ampere's force law in terms of the external product in R3. And the physicists, when they introduced what they called polar vectors, Vogt was a physicist in Göttingen, and also in the paper of Max Abraham in the Encyclopedia of Mathematical Sciences, they wrote about polar vectors, and these are essentially elements of the lambda 2 of R3, and they knew their relation to Grassmann. So it's not not every physicist knew it, but several of the important writers knew it. Minkowski introduced dual matrices. I will come to that close to the end of the talk. When he translated electrodynamics in special relativity, and the dual matrices of Minkowski, they were expressed in Grassmannian terms by Sommerfeld in 1910. They were called six vectors. These strange six vectors are elements of lambda 2 of the Minkowski space, or let's say, in Grassmann terminology, extensive quantities of the second level in Minkowski space. So, okay. And then, of course, you have complements that's already indicating in a direction which Atiyah's quote related to. Then Grassmann complements are just a mapping of these six vectors to these six vectors, lambda 2 of them to lambda 2 of them. Pauli, like Sommerfeld, used these dual complements. Kotler used a Maxwell tensor, etc. And so there was a kind of knowledge of Grassmann, but it was not, let's say, widely spread. Cartan, of course, knew Grassmann. And he used external products, and he even used Grassmann duality. I know he used the modernized term, Grassmann type of complements in terms of mobile frames. So in the paper of 1923-24, in dimension 3 and 4, that is classical and relativistic, and that's already going in the direction of general relativity and some kind of complement, which in a way was later Hodge duality in the generalized sense with regard to Grassmann. Okay, that was the first part, just to have this background on Grassmann complements. Now, my second part will deal with the birth of Hodge duality, not the development of Hodge duality. That's a huge, huge empire of theories, which I cannot cover by many reasons. The simplest is to say it's time, but it's even deeper. I understand too little of it. So it's easier to go to these early things. And okay. Hodge worked on algebraic and analytic geometry in the 1930s. Essentially, there are his most important works, and some come later. In a way, he revolutionized algebraic analytic geometry of complex surfaces and manifolds in these 2 decades, in the 1930s and 40s. Now, revolutionize is an easy word and used too often, so I put it in quotation marks. But the important thing is he generalized Riemann's theory of abelian integrals to higher dimensions. So in a way, what Jeremy just talked about Macaulay, that was an algebraic descendant of Riemann's theory. But here we really have the topological analytical theory, which was generalized to n dimensions. And that was not an easy task. He invented new topological methods for algebraic analytical geometry. So that's very much in the mode of the Riemanian approach in the complex one-dimensional case. And in Hodge theory, there were duality ideas at its core, namely the Hodge operator, which was a generalization of Grassmann complements, which he didn't know. He invented it, in a way he invented it new. A bit influence from physicists, as we shall see, but essentially it was a new invention by him. He didn't know Grassmann, as far as I can see. And then Hodge duality in the stronger sense, as a duality between the homology of a compact Riemanian manifold and harmonic forms on it. And that's again an anachronistic way of writing it. Here is the homology of the manifold, and the dualization is given by the by the harmonic forms. That's, in a way, that's the central theorem of Hodge. His background was, among others, Weil's book on the idea of the Riemann surface, Severius Lefschetz's analysis situs of topology of algebraic varieties, Cartan, the dissertation of de Rham, and de Rham in 31 dualized classes of closed forms and of closed manifolds, and he used, of course, much more. And the question is, which is somehow indicated by this Atiyah interpretation, is, was there Maxwellian electrodynamics a strong input at all? Was it motivation? What was it? Okay, we'll see. Just to indicate